Hello, my name is Alexander Jung. I'm assistant professor for machine learning at the Department of Computer Science in Aalto University, Finland. And I will now present our paper classifying partially labeled network data with the logistic network Lasso, which has been accepted for presentation at the ICASP 2020 in Barcelona. This is joint work with Nguyen Tran and Henrik Ambos. This work was supported by funding from Aalto University and the Helsinki Institute for Information Technology. The guiding principle of our work is to organize data and the associated computation as networks. Such a network structure is, for example, present in epidemiology related models and data where individual nodes represent persons or patients within a healthcare system, and these patients have some similarities. For example, within a virus spread, similarities between persons might be due to physical proximity. For example, when two persons had a joint lunch, then they might be similar, have a similar property or similar profile regarding epidemics. And we can encode these similarities conveniently using a network structure. So we connect similar data points by an edge. And the nodes in this network, they are characterized by many characteristics. So for a person, for example, a patient, we have a lot of features available to characterize that person. For example, we can use all the mobile phone data, which tracks the locations and the movement of a person. Also, any healthcare records about previous diseases, information about the age or the weight of a person. These are all features that characterize a data point. And in applications, we might be interested in finding out some other characteristic of a person, some higher level fact or quantity of interest. For example, we could be interested in finding out the probability that a particular person needs intensive care. This might be relevant for planning healthcare resources. So how can we learn or infer this probability of needing intensive care, so these hidden quantities based on the features that in principle we can observe or measure easily? And we will devise a method or an algorithm that finds out or estimates these probabilities of needing intensive care based on the features of persons and on the similarity relations between different patients. So, but in order to learn such a method, or how to design such a method, we need to have some information. We need to know something about individual, or at least some persons. So we need to know for some persons if they will need intensive care or not. And these labels, so this label information, we typically only know for few persons only. So we only know if a person needs an intensive care, if he or she actually needed a intensive care, and we then know in hindsight that the label was 1, so the person needed intensive care, or the label was -1, didn't need intensive care. And also, this label information is not exactly what we would like to estimate. So what we would like to know is the probability of needing intensive care. However, in hindsight, when we look at the hospitalizations, we only know if a person needed intensive care or not. So we only know this hard data or quantified data, quantized data. So what we would need is a model for the probability that the person needs intensive care. So the probability that the label is 1. And in our approach, we use a logistic regression model, which postulates this dependency of the probability of needing intensive care on the features of a person. So this equation here, so this logistic function maps the features xi of a person, so these are the features of a person, to the quantity of interest, so the probability that this person needs intensive care. And this model, or this classifier, is parameterized by a weight vector W. And the important point here is that we allow for a separate parameter vector for each person. So we learn a personalized healthcare model in some sense. And how can we do this? How can we possibly learn a separate model for individual persons? Well, we exploit the network structure. We postulate that similar data points or similar persons in this application have, first of all, similar labels, but not only similar labels, but actually similar models. So the statistical behavior of similar persons is similar, and we characterize or we quantify this similar or this clustering assumption. It's some form of clustering assumption that the persons in a cluster have similar healthcare models, and we enforce this clustering requiring a small total variation of the weight vectors. So these weight vectors, when we look at the differences over connected nodes or edges, then we say that the sum of these norms of the differences should be small. And this here is a form of total variation. So what we end up with as a learning criterion is a sum of two components. So the first component that tells us how good is a particular weight vector or model doing on the set of labeled data points for which we know the true label. So for these data points in telegraphic M, we know if the person needed intensive care or not. So we can compare how well does our prediction for the probability that this person would need healthcare matches the actual fact that it needed healthcare. So this is a form of training error or empirical risk, which we would like to minimize, but we balance this minimization of the training error by also requiring a small total variation. So we would like to have the weight vectors of well-connected nodes to be similar. And this balancing is implemented in a tunable way. So we have here a tuning parameter lambda, and this allows to choose between a focus on small empirical error. So we would like the learned models to extremely well agree with the observed labels, so with the actual hospitalizations. Whereas if we choose a large lambda, then we enforce that the models are more and more clustered. So they are constant over larger and larger components of the network, of the healthcare network, or the network of patients. So in the extreme case, if lambda is chosen extremely large, the solution of this logistic network Lasso problem will be a constant model. So we will be set back to the simple standard logistic regression model, which uses the same weight vector for all patients. Okay. Yeah, so this criterion is a convex function. It is a non-smooth convex function, so we cannot use simple gradient descent methods because the gradient is not defined, or this objective function does not possess a gradient at each point. However, there are quite efficient methods to solve such non-smooth optimization problems, and in particular to solve optimization problems which are in the form of the sum of two components, where each component could be minimized easily. So the first component here is this empirical error term, which is a continuous, smooth convex function, which we could minimize easily using some gradient descent or a Newton method. And the second term here is the non-smooth total variation component. So we can solve this coupled problem by looking at the dual problem. So we can use convex duality to define a dual problem, which is fully equivalent to the original problem. So from the solutions of this dual problem, we can extract solutions of the primal problem and vice versa, which I will show in a second in more detail. And this dual problem involves now parameter vectors that are defined over edges. So remember, the primal logistic network lasso was defined for weight vector or parameter vectors defined for the nodes in the network, whereas the dual problem uses parameter vectors assigned to edges of the network. And now one of the basic results in convex duality is a neat characterization of the solutions to the primal and dual problem. So we have that parameter vectors solve the primal problem, the logistic network lasso, and dual variables solve the dual problem if and only if these two inclusions or conditions are satisfied. So any pair of weight vectors for the nodes and parameter vectors for the edges, which solve the primal and the dual problem, must satisfy these two coupled conditions. And this already looks somewhat like a fixed point equation. The only difference is that here we have the element or the being element of operator instead of equality. But still, formally, it somewhat looks similar to a fixed point equation. And actually, it can be reformulated in a precise sense as a fixed point equation. And this fixed point equation can be iterated to obtain a sequence of primal and dual variables which converge to the solutions of the primal and the dual problem. And working out these iterations, so these updates of the fixed point equation, results in this algorithm 1, which is discussed in more detail in the paper. And what is nice about this algorithm, it can be implemented as a message passing algorithm. So all the updates here, it turns out that all the updates in this algorithm amount to local computations where each node has to update its state based on only on the neighboring, on the states of the neighboring nodes. So this algorithm can be implemented as highly scalable message passing over the data network. Yeah, here I have a simple animation which shows the convergence of the algorithm or the evolution of the predicted labels. So we only show the predicted labels, the quantified labels, as the number of iterations increase. And for this clustered network, we obtain a rather rapid convergence to the true. So in this case, the true underlying model was clustered, so constant over each cluster. Okay, so to sum up, we have proposed the logistic network lasso as a method to learn clustered classifiers from partially labeled network data. We have implemented the primal dual method to solve the logistic network lasso problem, and it can be shown that this primal dual method can be implemented as a message passing algorithm. And this message passing algorithm is guaranteed to converge no matter what the initialization is of this algorithm. Okay.